All right, so in the second part of chapter 22, we're going to talk about naming hydrocarbons, hydrocarbon reactions, and mainly, those two things. So first, we did talk about this last week with saturated hydrocarbons, and we mentioned, what does it mean to be saturated? Saturated means with hydrogens, so the most amount of hydrogens that something could have. So what that means is, for a hydrocarbon, if you look at these ones, there's none of these that are unsaturated, but since there's all single bonds and there's there's bromine, ignore the bromine. Let's just say every attachment to the carbons was hydrogen. Then they would all be saturated. An unsaturated is if let's say we take this one, that's an H, and that's an H. And then no, not that one. That one's the only one we can't do it to. This one. And then we just get rid of two of these hydrogens and we put in a double bond. That is now called an alkene. So Alkene. And that is ethylene. And it is unsaturated because you are taking away two of the hydrogens and replacing it with a bond. So you can do that. So those are saturated. Those are saturated are with only single bonds. And for these alkanes, a good formula to know for if you determine if it is an alkane from looking at the formula is CnH2n plus 2. So what that means is any n integer you put into that formula, let's say if it's butane, C4H10, right? So from knowing how many carbons it is, I can tell you off the bat what is the alkane version of it. So for like C5, pentane would be C5H12. So in this formula is conserved throughout all of the saturated hydrocarbons. Now, something else we mentioned is the more complex a hydrocarbon is, the higher the boiling point. So this stems from intermolecular forces, where even though they're nonpolar, they're going through our van der Waals and our London dispersion forces. The more London dispersion forces you have, when you have a bigger molecule, that means you're going to need more energy to break those bonds apart. Even though they're very weak, you're going to need more energy to do so. So that means, and they get to a point where it becomes pretty strong. Octane has more, or requires more energy to boil than water does. And that's because it has 8 carbons, where, water is a very small molecule, it has 18 molecular mass, but octane has 8 carbons and 18 hydrogens. So it takes that many atoms in one molecule to overtake the strong hydrogen bonds of water in a water-water interaction. So this just goes to show you, when the size increases and the molecular weight increases, the boiling point also increases for hydrocarbons. And that's exactly what I just said. And usually they're less dense than water because there's no strong intermolecular forces between them. There's only these dispersion forces. If you had stronger molecular forces, then it would be more dense because it would be the intermolecular lattice of the alkanes or any hydrocarbon would be more attracted to each other, more closer together. Okay, so here's the names of the main alkanes. So you have, I went over the prefixes last week, but it's good to know them. So you have meth means one carbon. Methane means 1 carbon with 4 hydrogens. Then you have ethane, which is 2 carbons, 6 hydrogens. And you have propane, butane, pentane, etc. Now, the reason why it says this N, that stands for basically normal. And yeah, I took attendance. So that stands for normal, meaning the straight chain version of butane or pentane. Now, I did mention last week, but we may have forgotten, that there are isomers. And one of the isomers of butane is called isobutane. And there could be 1 methyl, or it could be 2 methyl pentane, for example, or different types of pentane. Or it would be 2 methyl butane, which would be the same number of carbons as pentane. But the point is that this N means that it's the traditional straight chain. Okay, so here's more of them. So there's N-hexane, heptane, octane, nonane, decane. So those are just the straight chains of them. And they all follow the formula CnH2n plus 2. Any questions on the alkanes? No. Okay, so now we're going to learn how to name them. So here's some uses. So let's name them. So there's the IUPAC. That's the International blah, 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 blah naming, whatever, of the American Chemical Society. Okay, so there's a naming scheme for all of these organic compounds on how to name them. And they're very fun to name. It's like a puzzle. Very fun. Much more fun than ionic and covalent. So you have for alkanes, every one of them ends with A-N-E, like alkane. Yes, Christina, very fun. Then you have the substituent. When I was in undergrad, I would call this word the substituent. It's substituent. And my professor would look at me like, what? So it's substituent. And I've actually said that word, substituents, into my PhD. And I've then looked at, then I heard someone else say it. And I'm like, oh, that's it. Substituents. Got it. Then it makes me feel more distinguished saying that word when I'm going over my organic synthesis, because I say, if you look at this methyl substituent right here, and it sounds better. So anyway, a substituent is a group of atoms or some kind of chain that is on the side, otherwise known as a side chain. We call them commonly side chains. And if you have, let's say, we really use the word side chain for amino acids. If we have an amino acid chain, let's say we have a serine, then it has a methyl as its substituent, but it's a side chain. All right, so we'll go over what these side chains mean or what they are. They're basically just offshoots. So if you had a propane, or so let's say we had butane, right? 1, 2, 3, 4. We can have 1 methyl butane, all that, or 2 methyl butane. That means right there. So we're putting a methyl at the position here. And the way we numbered that position, I just called it 2-methyl butane. The reason why is because we always start the numbering of carbons at the lowest number for the substituent. So we wouldn't name it 1, 2, 3 going from left to right, because we don't want it to be 3. It could be 2 if we go the other way. So it'd be 1, 2, 3, 4, meaning it's butane. And then it would be 1, 2 is where the substituent happens. So it would be 2. And what is that substituent? It's just a CH3. If you remember the shorthand stick diagram from last week, this is only a methyl. So it would be 2-methyl, because 2 is the position. Methyl is what occurs at the position. And then the rest of the longest chain, which is 1, 2, 3, 4. So 2-methyl butane. And we'll see this as we go forward. That's just an example. Now, prefixes, here we go. So meth, eth, prop, but, pent, and then it's just the shapes after that. So, yeah. And then, so here's names of the group. So I used the word before when I drew this example. I didn't write 2-methane, even though this CH3 is technically, it's a methane, right? But methane itself is CH4. So having a group that basically is methane, but on the end of a organic structure, we call it a methyl group. So there could be an ethyl group, a propyl group, a butyl group. That means you have every carbon is exactly the same. You have the correct number of carbons and hydrogens, but you're missing 1 hydrogen at the end where that substituent binds to the rest of the structure. So those are your prefixes, and those are important to know. Those won't be given. So here are some of them. You have methyl, ethyl, propyl, butyl, but then you can have isopropyl, meaning this part is bound to another structure. And then you have pentane, but instead of being a straight line like propyl, it's called isopropyl. So that means it's each of these carbons are isolated from one another. So isopropyl. And this is where you get isopropyl alcohol or 2-propanol. So isopropyl alcohol, which is IPA, which is commonly used for cleaning things because you're antiseptic to clean, it would be like that. This would be isopropyl alcohol, or another name of it is 2-propanol. Then you can have an isobutyl group. You have a sec-butyl. So sec means secondary. And you have tert, which means tertiary. So an isobutyl, meaning this middle carbon is being isolated from the other, or is isolating the other 3 groups. Then you have a sec-butyl, which means 2 out of the 4 carbons are in one chain, and then 1 is in the 3rd chain. Then you have a tert-butyl, which means that they're all isolated, kind of like an isobutyl. So tert-butyl and isobutyl are similar because technically these are the same. These are very, very similar. It depends what you have here. So anyway, moving on. So naming, here's the notes on how to name it. We'll walk through this, but then we'll just do some examples. So naming alkanes. Identify the longest continuous carbon chain and determine the base name of the compound. So let's do this one together. So if you can see this, we have how many carbons in the longest chain? 1, 2, 3. Good job, Christina. 4, 5. And they have it highlighted for us. That's great. Or we could have 1, 2, 3, 4, 5. There's 2 different ways to do it. Because there's 2 different ways to do it, they're both the same. If there weren't 2 different ways to do it, then they'd be different. And if you go the other way, backwards, it's still the same thing because this substituent is right in the middle. Okay, so then what, does anyone want to come up with what do we do with it? Like how do we name it before we go through all the rules? No? Okay, we'll go through it. So name the branches as alkyl group. So alkyl group is another name for just a saturated hydrocarbon, alkane. Alkyl, alkane. If more than one type of substituent is present, name alphabetically. Number the chain from the end closest to the branch. If the first branches are equal distance, use the next substituent. So what that means is, let's say we had a thing and you had 2 substituents here and then 1 here and 1 like that. So what you would do is, let's say these 2 are the same distance from the end. So you're like, which one do I use first? You use the one that has the second closest substituent, and that would be this side. So this side would be 1, 2, 3, etc. Okay, then you write the name of the compound in the format substituent number, substituent name, base name. And we'll go over that. And then use prefixes if there's more of the same one. Okay, so with that information, we know that since the longest chain is 5, we have pentane. Okay, we have pentane. Now, what type of pentane? What else is going on? Can anyone answer? So if we go from counting 1, 2, 3, what happens at 3? Substituent of propane. Not propane. It's only 2, right? So the substituent counts what is not part of that chain, what is offshooting from that chain. So good, ethane. So ethane with the A and E is the completed molecule. This is just the side chain. Exactly, Ronit. So that's ethyl. So it'd be an ethyl group. But not just any ethyl group. Where does this what number does the ethyl group occur at? 3. Good. 3 ethyl. So the name would be 3 ethyl pentane. And it's ethyl because the offshoot, the substituent, has 2 carbons. So you look at whatever is bound to the main chain, the longest chain. And no matter how you draw it up, because this is a symmetrical molecule, you will get 3 ethyl pentane every time, no matter where you count from. But that's not always the case. So we're going to have to pick where we count from in other examples. So we're going to do another one, because I can tell that some of you are a little bit confused. How can I tell through Zoom? I don't know. Okay, so I'll make one up. Okay. Wait. There we go. All right. We got to name this. Oh, I'm going to throw in a curveball. There we go. All right. We got to name this. So the first thing, can someone tell me the longest carbon chain? How many is it? 7 carbons. 1, 2, 3, 4, 5, 6, 7. Nice. All right. So that means it's a heptane. So we can write down heptane. Now, at which number or where is the, so which side of it should we count from, the left or the right? Where should carbon number 1 be? The right, Naomi. Good. Tariq, good, good, good. Right. Awesome. And Christina, a little late to the party there, but good. So we can name it from the right because the right has the lowest number substituent. So you have 1, 2 is where the first one occurs. 3, 4, second one occurs. And then 5 is where the third one occurs. 6, 7. All right. So now we can start naming our substituents. You see how fun this is? So let's count through 1, 2. So 1, nothing. 2, what do we got? We got something at 2. What is it? Methyl. Good. 2. Methyl. Next, 3, 4. 4, what do we got? Ethyl. 4. Ethyl. 5. We got something else. What do we got at 5? Anybody have any idea what Cl would be? Close. It's not chloride or chlorine. Not chloride. Propchloride, good guess, but no, it would be chloro. So just chloro. Chloro. And then nothing at 6 and 7, and you'd have heptane. Monochloride. Not bad. Not bad guesses, guys. But we didn't learn this part yet. We're going to learn it next. So now you'll be prepared for it. All right. So how do we name that? How do we put all of these together? We go in alphabetical order. So 5-chloro, 4-ethyl, 2-methyl, heptane. That sounds like a lot, but if anyone were to see this, they'd be like, all right, heptane comes first. They would draw the 6 lines. Then they would say, all right, at position 2, we put methyl. 4, ethyl, and 5, we put chloro. So the answer would be 5-chloro, 4-ethyl, 2-methyl, heptane. Why is it not numerical order? Good question. It's because they like alphabetical better. And also, here's another rule about the alphabetical. That when we have 2 of the same, and yes, so heptane is last because heptane is the root, is the root of the entire thing. It is a heptane. It's not a propane. It's not an ethane. It's not a methyl. It's not a methane. It's the skeleton of this thing is the heptane. Right, exactly. It's the longest carbon chain. So then everything else has to be alphabetical around it. So something else that doesn't count for the alphabeticalness is the prefixes. So we did not encounter, let's say we had a chlorine here and a chlorine here. Let's say we did that, right? The name would be 3, 5, 5 trichloro ethyl trichloro 4-ethyl 2-methyl heptane. So that's weird, but you can have multiple substituents of the same type, and you can just list what numbers they're at. The commas indicate what positions they're at. So 3, 5, 5 means there's 1 at 3 and there's 2 at 5. And then you have trichloro, so you need to tell the reader that there's 3 chloros here, but just to make sure there is, I'm going to write trichloro. And in that case, the trichloro, the T, doesn't count in terms of alphabetical order. It's usually whatever's after the prefix is first. So yeah, these names can get long quick. Okay, so the 2-methyl, so we're counting from this side. The reason why is because we want to count from the side that has the lowest number substituent. So if we count from the left side, we have 1, 2, 3 is when the first thing happens, the first offshoot. But when we're counting from the right, we only have 1, 2. So that's where we base our numbers from. So we have 1 is the end carbon. 2 is this carbon right here, which has an offshoot. So we name it 2-methyl. Then we have 3, 4. We have an offshoot there, which is 4-ethyl. And then we have 5-chloro. All right. Any questions on that? Good. All right. Okay. So we talked about alkanes. Now we're talking about alkenes. So alkenes are the double bond form of alkanes, the unsaturated version. So a simple formula would be the main formula would be CnH2n. So it's not 2n plus 2 anymore, because to get from, let's write C2H6, that is ethane. 1, 2, 3, 1, 2, 3, ethane. Then you have C2H4 is ethene. The reason why it's ethene is because you can see where those 2 hydrogens get removed. They get removed here, and what gets put in place? A double bond. So that would be ethene or ethylene. That's another name they call it. So that's what it looks like. And then we can name different alkenes. So with alkanes, we start off with the ANE. Now we make the ENE with alkenes. So we have the same name, same exact thing. We have ethene, propene, 1-butene, 1-pentene, 1-hexene, etc. So the reason why there's asterisks near it, next to butane and pentane and heptane and hexane, is because we now add this 1 in front of it. So that 1 is exactly what it sounds like, positioning. So it's 1-butene. That means what is the positioning of what makes it butene? What makes it butene? 4 carbons. What position out of those 4 carbons is the butene part of it, the double bond? Number 1. So you can tell, all right, from bond number 1 to bond number 2, or carbon 1 to carbon 2, you have 1 pentene. It could be 2 pentene. That's what the double bond's right here. Can't be 3 or 4 because then we just flip it around and it's 1 and 2 again. Same with hexene. It depends on the position of the double bond. Okay, any questions? Wrong name. Did I get something wrong? No. Oh, okay, it's okay. Okay, so next, the alkynes. So we talked about that hierarchy of bonds. We have single bond is alkane. You have butane, propane, etc. Double bond, you have ethene. You have the ENE. And then alkynes, you have the EY, or the YNE, not the EY, the YNE. And that formula is predictable because you're going to be putting in another bond and getting rid of 2 hydrogens. So it would be CN and then H2N minus 2. So minus 2. Now that we have 2 less oxygen, less hydrogens than the other ones, than the ethene. So here's some alkynes. You have ethyne, propyne, 1 butyne, 1 pentyne, 1 hexyne. Same rules apply where this triple bond could move, or it could not. It can't move. It could be anywhere in a structure you're looking. So not normally on the end. It could be 2 butyne, pentyne could be also 2, hexyne could be 2 also. Okay, so for which formulas of the 3 non-cyclic hydrocarbons are listed below, which of them is an alkene? And we have C. I like the answer for C. C is a good answer. All right, so it's C. Let's draw it because we have the first of all, the formula CnH2n. That's the formula for alkenes. But if you can't figure that out, we can just write it 1, 2, 3, 4, 5. And let's count them up with the hydrogens. Oh, that's not right. So we can go. So if we have full saturation, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's too many. We want 5, or we want 10. So if we removed one of these and added a double bond, or removed 2 of the hydrogens and added a double bond, you would get an alkene, and you get pentene. All right, any questions on that one? And there's some alkynes, naming alkynes. So the naming works the same way as for alkanes, except, they say except. So the base chain is the longest continuous carbon-carbon chain. Okay, we know that already. So basically, they're just saying that not just with alkanes, but with all of these, it's the longest carbon-carbon chain. And then you number the chain from the closest to the multiple bond. Then number in front of the main name includes the first carbon of the multiple bond. Okay, yeah. Right. So if you have, let's go back to that pentene example. This molecule would be called 2-pentene because you have carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. It would be 2-pentene. Well, Tariq, there also could be substituents here also. But in this case, we're saying if there's double bonds or triple. So with these double bonds, we can declare an orientation. Wait, hold on. We got the base name is just the number with the double bond. Yeah, so Tariq, when there's multiple bonds, you start at the first carbon that is double bonded to the next carbon from the shortest side. So it sounds like we need to do examples. Well, I do want to do an example anyway. So let's do, no, we'll do that. Okay, so we have shortest side or longest side is starts from here, and then the shortest length to the substituent is right here. So we would have two chloro, one, two, three, four, five, six. Like that. So 2 chloro, 2 hexene. Oh, did I write hexane? Whoops. This would be 2 hexene, like that. Okay. Moving on. Isomerism. So the cis and trans isomers can happen across a double bond. This means you can have 2 separate molecules that can do completely different things based on their cis-trans isomerism. So here's an example of the trans 1,2 dichloroethane and the cis 1,2 dichloroethane. And you can see they're bonded very similarly, but the carbons are just flipped over. And this has a big effect, believe it or not. And it has an effect on your understanding of chemistry and the density a little bit. Density is about the same. Melting point has a difference and boiling point has a difference. So the density is about the same because, I mean, they're the same size. Yeah. There's a little mass defect difference. Okay. So let's talk about some hydrocarbon reactions real quick. So combustion is the most common, but we're not going to go over that since we've already covered combustion a lot. Halogen substitution is where with additional heat, these are what am I going to say? These aren't spontaneous reactions a lot of the time. So with additional heat, you have methane and chlorine. They're going to mix together to make chloromethane. If you did it again, you'd make dichloromethane. Again, you'd make chloroform. So you can do this reaction to make chloroform. And then we have the general form of this. So basically what's happening is in organic chemistry, there's 2 terms, the electrophile and the nucleophile. So an electrophile is something that wants to pick up an electronegative atom. So let's say it's carbon is pretty good at that. So let's say carbon's looking for stuff. And then chlorine, when you heat it up, you're breaking bonds. So the chlorine bond will break. And then the electrophile, meaning the C and the CH4, will drop a hydrogen in order to take the chlorine. And then you end up with CH3Cl. So that's alkane halogen substitution. Okay, moving on. So there's other reactions that can happen. We're not going to go too crazy in depth. Remember, mind, this is just a kind of cherry picking lesson into organic chemistry. So we have hydrogenation. So we're adding H2 and we can saturate different hydrocarbons using a catalyst. Usually it's a metal catalyst like platinum. If you put a piece of platinum in a solution with, I don't know, like an alkene with double bond, you will strip off those hydrogens. They'll turn into more hydrogen gas, and then these hydrogens will then bind to it. Okay. Then you have halogenation. So we're adding the halogen, the diatomic halogen, and like we saw before, that's halogen substitution, basically. So you're substituting one of the hydrogens in your molecule for a halogen. And then you have hydrohalogenation, which means that what happens is that the negative charge, since the acid is so polar, the positive charge from the halogen will bind to the carbon immediately, and then the hydrogens will go with the whatever X is. If it's OH, then it makes water. We're all happy. So here's some other reactions. Aromatics. So the aromatic hydrocarbons are pretty important. They have an aroma, they have a smell, they have electron absorbing. We have a absorbance absorbing property. And electron and light absorbing property. Sorry, that's what I meant to say. And then, so what the aromatic is, it is either a 5 or a 6-membered ring with alternating double bonds. And here's benzene, the most common aromatic around. So you can have resonance from these aromatics, which I've mentioned. And then you can also do halogen substitutions with them, or any kind of substitution you wish. So what would happen is you would end up with a chlorobenzene. Instead of just a benzene, it'd be chlorobenzene. And then you have other things as well. You have ethylbenzene, bromobenzene, etc. Examples, yes. All right, so I'll give you an example. Let's see. And we also draw them with these circles in the middle, like a little birdhouse. Okay, so here's our example. So what do we got? We have a benzene on the end. We have one carbon. Well, how many in the straight chain? We got 1, 2, 3, 4, 5. So if it's 5, that means it's going to be what kind? Good. It'll be a pentane. So there's different ways to name it, but we could use either the 5-membered chain as our base, or we can use the aromatic ring. That's what we learned here. So what we can do is we can say that this is going to be carbon number 1, and then we can say, where's everything else? So here's carbon number 2, 3, 4, 5. Actually, wait. It'd be moved down 1. It'd be 1, 2, 3, 4, 5. Okay, so you'd have 1 methyl, then you have another 1 methyl. So it'd be 1, 1 methyl. 2, you have a chloro, so that comes first. Why did I do that? Chloro 2. Hold on. I'm like losing it here. 2 chloro. And then you'd also have, that's it. Yeah, so it'd be 1, so it'd be 2 chloro, 1 methyl,
Wait, Professor, why aren't you counting the carbon before the substituent on the left?
You mean here?
Yeah.
That's part of the benzene.
Okay.
So what we're going to name this whole thing is a propyl benzene. No, sorry, a hold on. Pentyl benzene. It's weird to say. I've never seen a pentyl benzene before. But yeah, that would be it. Pentyl benzene. Yeah. Okay. So it would be the whole thing is a pentyl benzene. 1,1-methyl, 1,1-dimethyl, sorry. 2-chloro would be first. So it'd be 2-chloro, 1,1-dimethyl pentyl benzene. That accounts for everything. Okay, that was kind of big. Any questions on that one? It seems the same. Hopefully that means good. Did you get it? Okay, good. Yeah, it's the same kind of scheming. Okay, good. All right, so here's some examples. So when a benzene group is not the base name, so there's different ways to name it. This is where it's tricky. It's not always one correct answer. But if let's say you have a benzene that's in the middle of a chain, you call it a phenyl group. And what a phenyl group is technically this whole thing is a phenyl group. So like phenol, it kind of stems from phenol. Phenol looks like this. But it's a phenyl group. So you can say that it's 3-phenylheptane. 1, 2, 3, 4, 5, 6, 7. So 3-phenylheptane. This is 4-phenyl, 1-hexene. Because you have 1, 2, 3, 4, 5, 6. Oh, look, double bond. And that means we start the chain at the side closest to the double bond, which is this one. So it would be 1-hexene. And then you have an attachment at carbon number 4. And it's 4-phenylhexene. It wouldn't be like benzyl. Well, you could have benzyl. That's the thing. Like there, it could be called benzyl, but phenyl is the correct name for it. Phenylhexane or hexene. Okay. So naming benzene. So we can actually name why isn't the hexane first? What do you mean? Because so hexane is the root, is the longest chain. Wait, what? Isn't it closer to the double bond? Okay, wait. So no, the numbering, we start from where it's closer to. So numbering. So that means this is carbon number 1, 2, 3, 4, 5, 6. Then we just name our substituents. So it'd be 4 is the only one. So 4-phenyl, 1-hexene, because the 1 position is where the hexene occurs. Does that make okay? Good. Cool. So then we can name things on benzene itself. So we can name substituents on an aromatic ring very easily. So all we would have to do is number the ring starting from the attachment for the first substituent, then move towards the second. So what that means is usually it's the one that is alphabetical, in alphabetical order, first in alphabetical order. And then if it's di, they're the same. So it doesn't matter which one. So let's say if you have like chlorine there and a chlorine here, those are the same. You can start from either one or the other because they same thing. Okay, so for these examples, you would start from the substituent that has the lowest alphabet. That would be first in alphabetical order, which would be a chloro versus an ethyl. So it'd be the chloro. So start from chloro, and then you count in the direction that will give you the lowest number substituent for the next one. If it's at a 4 position, if it's like a 1,4, that's okay. And there's names for that too. We'll talk about that soon. But usually you want to aim for minimizing the numbers. So it would be 1 chloro, 3 ethyl, which is this one, benzene. Benzene's the whole thing. So if you break down, I feel like the names are going to be easier to go from names to structures than structures to names, because the name outlines it for you perfectly. So the next one, okay, so chloro comes first because alphabetical order. It's always alphabetical order. So now you see in the next one, chloro does not come first because it's second in alphabetical order next to bromo. So the bromine is going to be 1, chlorine 2, then we go clockwise 3, 4, 5, 6. And then you can start naming. So it would be, it's a benzene, it's a chlorobenzene, or it's a 1 bromo. That's what happens first. And then we have a 2 chloro. So it'd be 1 bromo, 2 chlorobenzene. Any questions?
I just have one question. So how come, I'm sorry if you hear my brother screaming, but how come the chloro takes the benzene and not like the bromo?
Oh, because it's last. So it's a good question. Because it's last in the order. So you could technically write it as just chloro with a dash benzene, but normally we just put those two together. Whatever's last with the root word, it goes together.
Okay, and then we
it's based purely on the alphabetical order.
Okay, and then like to identify like the root, the root chemical or whatever, we'd have to memorize those.
The main ones with the anes, like the anes and the enes, like the alkanes, the alkenes, and the alkynes, yes. And I would say benzene, but that's it. Because every other one, you're really not going to see that. And then we're going to learn about functional groups, which makes it a little bit more complicated. Wait, so Christina, sorry, the benzene is the right ring. I mean, right. I mean, all these are benzene rings. Oh, wait, ring, right. Okay. Ring, right, ring. Okay, you're confusing me. All right, let's go. Continue. Okay. Where's my mouse? There it is. Is the ring right? You mean?
She's just saying, is the ring itself the benzene?
Yes. Yeah. It is. It is. Okay, so then we can have multiple substituents. Then it gets more. I'm sorry. See, orgo sucks, right? Okay. It gets worse. Then you can say, what if you had 2 of the same substituents? You could do it like we normally have been doing. So let's say we had this, the first one on the left. 1, 2 dichlorobenzene. That makes perfect sense, right? Because you have, all right, it doesn't matter which one you start from. You goes 1, 2, 3, etc. Yeah, 1. Yeah, exactly. You use commas. 1, 2 dichloro, got that part. 2 chlorines, benzene. Check. But then you can say that there are funky names for those positions. And there are. If you have 2 substituents that are the same, or that are not even the same, they could be different too, really. And they're next to each other. They're 1, 2. You can call them ortho. So that means 1, 2. So you can have ortho, chloro, and it wouldn't be benzene, it would be toluene, because toluene, well, wait. No, it'd be benzene. Toluene's different. Why isn't it? Why does it say toluene? Hold on. No, it would be benzene, chlorobenzene. So toluene is this. It's a benzyl with a CH3 group on the end. So I think, no, this wouldn't be, well, technically this name works too, because to the reader, it assumes that the CH3 group is substituted for a chloro. But if you write orthochlorobenzene, that works too, or metachlorobenzene, same thing. Parachlorobenzene, it means this. So same thing. So you have those three terms. Ortho means next to each other. Meta means one away. And para means opposite. Para is the easiest one to remember because it sounds like maybe parallel or whatever. But it's the opposite side. Okay, so I would say don't stress these too much. You're not going to see them. I would say know about the numbers and know how to generally name something from the numbers. When it comes to aromatics, not necessarily the ortho, meta, and para. So then you have you have polycyclics. We're not going to go over that too much. Then you can have reactions with aromatics. You can do a substitution. So any of the hydrogens that are placed. And yes, it's about position, Tariq. So number in terms of like the bond distance, meaning is it one bond away, two bonds away, etc. So you can have substitutions, which are just, you can add it with a halogen, and then you can replace a halogen in for a hydrogen. Then the last thing we're going to learn are the functional groups. Now I have a really good crash chem video just highlighting the functional groups. Hashtag crash chem on Instagram. So a very good video just goes over them in 30 seconds. Now the functional groups are groups of atoms that have a specific function. Wow, no way, really? Yes. So here they are. This group is missing one of them, this table. So here's the main ones we're going to learn. We have alcohols, right? The ones that you drink and the ones that are poisonous. Ethers, aldehydes, ketones, carboxylic acid, esters, amines, and also this one that's not listed here, amides. Oh, thanks. I appreciate that. So then an amide is RN C double bond O R. So that's an amide bond. Okay. Did I put amided? Oh my God, I'm losing it. This is amide. Okay, so here's all the different functional groups. Oh, you did a lab on esters? Good. They smell good. All right, so if you were in class, you got to smell them. All right, alcohols. Alcohols, you drink them, but sometimes they can kill you. Well, even if you drink them, they can kill you if you drink too much. Yeah, you virtually smell them, right? So ethanol is the alcohol that is in our alcohol, the drinkable alcohol. Isopropyl alcohol is for disinfectants, which can kill you. Methanol causes blindness. So they're a couple of carbons away and structurally bit similar, but they all do very different things. So if you want to know where that proof comes from for the alcohol, like if you have 110 proof whiskey or whatever, that means it's the percent alcohol or percent ethanol times 2. So that's a fun fact. But these ethanols or alcohols, they give the structure, or they give the they have several functions. For one, they increase the vapor pressure or decrease the vapor pressure because they make molecules more polar. Because you're adding an OH group, you're making it more polar. So in terms of naming, you add and you add anol on the end of it, right? So instead of butane, it would be butanol. So let's say butane becomes butanol. So there's not many things, not much more than that. So here's an example, like you have isopropyl alcohol, otherwise known as 2-propanol. And well, let's write that one because that's important. So 2-propanol, what that means is propane, right? Carbon, carbon, carbon. Propanol, an OH group on the end of that. So this is carbon number 1, carbon number 2, carbon number 3. 2-propanol means, oh, the OH is not here, it's in the middle at position 2. So this is 2-propanol. And it also means isopropyl alcohol. Why? Because this position is an isopropyl because it's separating the 2 methyl groups out of this carbon. So it's an isopropyl, and then the remaining is alcohol. Both the same thing. And does the butane become butanol? Yes. So if you have butane and you just take away one of the hydrogens, put an OH on it, butanol, 1-butanol. You can have 2-butanol or 1-butanol. You can't have 3-butanol. All right, so that's a good question that I just thought of. Why can't you have 3-butanol? So if you're looking at the bottom, you see 1-butanol. I said you could have, see, 1-butanol, 2-butanol. Why can't you have 3-butanol? Anybody? No space. Not really. Think about symmetry. Yes, Sebastian, good job. Because it would just be 2-butanol again. Because look, if you flip the molecule around, look, there's 4 carbons, right? So it's symmetrical in the middle. If you put an OH here, it's the same thing as putting an OH here. So it would be 2-butanol again. And then if you put it on the end, it wouldn't be 4-butanol. It would just be 1-butanol again. So that's what you can do with alcohols and with really any of these functional groups is you can attach them to different carbons. And it's important to keep the symmetry in mind when we're going through these structures. That's what makes it kind of fun. You have to look at symmetry and kind of like flip them in your head and kind of see what's going on there. So naming them, the main chains contain OH. Number main chain from end closest to OH, like we did. Give the base name and OL ending, and then place the number of the carbon, indicating where the OH is attached to it. So that's what we kind of did. And there's several reactions they can go through. You get a substitution where like a methanol becomes a chloromethane and water. Acid catalyzed elimination, which is just like a dehydration synthesis, meaning water comes out and then you create basically the alcohol goes away and you create an alkene. There's several reactions. Then we have oxidizing and reducing. So that's a big thing in organic chemistry to understand is oxidation and reduction. So all we have to know is that we just learned, we're in the middle of learning the hierarchy from the most reduced hydrocarbons to the most oxidized hydrocarbons. So if you think about oxidation, what does that mean? You are either adding oxygens or removing hydrogens. So the first thing we started out with was the most reduced, meaning an alkane, right? The most reduced. Then we oxidized it a little bit, right? Because we went from there to an alkene. Because an alkene is oxidizing, right? You're removing hydrogens. Becomes an alkene. Then we can go from, well, let's say we went back to an alkane. We can just gain oxygen and become an alcohol. That's oxidation. Then you can either gain alcohol or gain oxygen or lose hydrogen. Let's say we lose hydrogen to become more oxidized. We get to an aldehyde. And then we can go from an aldehyde to a carboxylic acid by oxidizing again. So it's a hierarchy of reduction to oxidation, or most reduced to most oxidized. So that's what we can do with these, and we can do that for a lot of them. And even for the amides, we can do that. Okay, so let's get into those last two. They have that in common. So from the list, there are several with this C double bond O in common. Aldehydes, ketones, carboxylic acid, esters, and also the amide, which is down here. They all have that in common. And what is that? That is a carbonyl group. So that umbrella term, carbonyl or carbonyl, how some of my colleagues call it. I think my advisor says carbonyl. I like carbonyl better. It's probably carbonyl. Whatever. Say as you wish. So the carbonyl group means it's just the C double bond O. That's all it is. The C double bond O part of the chemical or the reagent of the structure is the carbonyl group. The question you'd have to ask yourself is the carbonyl group part of a larger functional group? And usually it is. So it could either be an aldehyde, a ketone, an ester, an ester, or a carboxylic acid, or an amide. So you have a lot to choose from. So here's some examples of aldehydes. So an aldehyde is formaldehyde, is one of the most common ones. And it's one of the most simple ones. So here's formaldehyde, or methanol. So formaldehyde is this. And an aldehyde group is just this part. So it's not even written here. It should be. But if you have C double bond O, you have an H on one end and an open group. It could be anything on the other end. That's an aldehyde. And to name these aldehydes, you take the number of carbons that they're in, starting from the carbon where the aldehyde is present, because they usually occur at the end, or they have to occur at the end of the molecule. So that's easy. So you assume it's 1. And then you write the number of carbons followed by an Al, not an Ol, like the alcohols. So this would be methanol. And you can break that apart into a funny word, but but methanol. And then that's about it. So then a ketone is different. So an aldehyde always happens at the end of the molecule because it has a cap. The H, think about the H as a cap. A ketone does not have a cap. It is a carbonyl group with an R group on one side, R group on the other side. So it can keep extending whenever. So that's a ketone. And this one is an aldehyde. And to have the name of the ketone, we'll see that later on. And you just add the O-N-E. Instead of Al, it's like butanone, for example, or methanone. They add oxygen. What do you mean? Yeah. I mean, you're adding the double bond oxygen. So I think so. So here's some examples. And yes, ketones, keto. And those are released when someone's, they're like when someone's hyperglycemic. The ketone bodies. Ketoacidosis, exactly. Okay, so here's some common ones. So you have acetaldehyde, which is like acetic acid, but as an aldehyde, which is also called ethanol. Then you have propanol. Then these are the 2 and 3 carbon versions of the aldehydes. Then you have the ketones. So you have acetone, which is one of the most common ketones, and then it has butanone. So there's only one butanone because this C double bond O could either go between this bond or between the other one. But then you can have, when you have more carbons, let's say we have 5, 1, 2, 3, 4, 5, we can put the ketone there. And that would be called 2-pentanone because it's a ketone. And you could either have that, you could have like 3-methyl-2-pentanone. You could have 4-chloro-3-methyl-2-pentanone, etc. So the most important thing for naming organics is finding the root word and then building your structure from there by the substituents. All right, so here we go, naming the aldehydes and ketones. So basically what I said already, but for aldehydes, give the base name with an AL ending, always on the first carbon, always, because it always occurs, the aldehyde portion of the compound always occurs on the end. So you have to name it from that side as carbon 1. For ketones, give the base name with an ONE ending and place the number of carbons on the chain where the C double bond O is attached before the base name. So that's like we did before, where here carbon number 2 is where we have the ketone. So it would be 2-pentanone. So there's several aldehyde and ketone reactions. You could do reduction. You can do reduction to an alcohol, and then reduction further into an alkane. And then you can do addition reactions. So here's an addition reaction. You can add the cyanide ion. This is hydrocyanic acid. And what happens is the hydrogen, it becomes a partial bond, and the hydrogen is a nucleophile, or sorry, electrophile, and the oxygen is a nucleophile. It looks for hydrogen, finds it, strips it away, then this carbon becomes a nucleophile or electrophile for the cyanide. Carbonyl groups, here we go, it's just the polarity of it. So these organic molecules, before we talked about organic molecules that are not very polar, these are pretty polar. I mean, you're going to have, depending on their chain length, the longer the hydrocarbon chain length, the longer it is, the less polar it is. Because the more nonpolar things you put onto a compound, the more nonpolar it's going to be. So generally, CHs are not polar. But the more oxygens you put, the more polar it's going to be. So for larger, more complex organic molecules, you can have both polar dipole interactions, hydrogen bonds, van der Waals forces, all happening at the same time. So for example, in my research, the compounds that I've developed, they partake in hydrogen bonds, they partake in van der Waals in some parts of the molecule, and they partake in ionic interaction with another part of the protein. So these can all happen at once, especially when you get to more complex functional groups and putting more than one functional group into a molecule. All right, so one of the last ones, you have carboxylic acid. So carboxylic acid, as you can guess, makes organic molecules more acidic. And you can change the name by making it oic acid. So benzene, one of the most common weak acids in organic chemistry, if you make benzene into an acid, it becomes benzoic acid. And it looks like this. Like that. Cool. Yeah, I'm sorry there's so many functional groups. But yeah, so that's the carboxylic acid. And you could do it propanoic acid, butanoic acid, etc. So here's some of those carboxylic acids. Ethanoic acid, butanoic acid, methyl butanoic acid, or no, methyl, or was there, sorry, this is the bottom ones are the esters. So any questions about the acids first? No? Okay. All right. So going on to esters. So esters are a carboxylic acid, similar. So you have a carboxylic acid, but instead of putting the hydrogen on the end of the oxygen, you have it open to an R group. So it's an ester. That's what an ester is. So an ester, they end with the O8 ending. So you can have methyl benzoate. Methyl benzoate looks like this. There's a benzene, and it usually goes, the carbon comes first this way, and then it becomes methyl benzoate. That means you have methyl, benzene. So, and it's between an ester, so methyl benzoate. So yeah, with the homework, you'll have time to practice these. And also next week, you know what I can do? I could extend the homework until the last day of class, or the 12th, until your final. So then next week we can work on that too if you want to practice this more. Examples of naming carboxylic acids, and we went through this already, but here's methyl butanoate, ethyl propanoate. So there's that. Carboxylic acids, so they're weak, sour tasting, vinegar, formic acid, which is in ants and some wasps, citric acid in fruit. They're just a lot of the organic acids that we consume. Esters have a sweet odor like pineapple, things like that. And then you can have different types of reactions with acids and alcohols to create esters. So what happens is this is a dehydration synthesis reaction where the alcohol's hydrogen or the alcohol's OH and then the acid's hydrogen will come off and bond together, create water, and then the R group will be attached to the remaining oxygen from the acid, which will create an ester. So that's all possible. And here's again an acetate and a salicylic acid. And this is an aspirin. So acetyl salicylic acid is aspirin, and that's how it's synthesized. Both of which, these are very cheap products, so you can buy them. Okay. So back to the oxidation reduction thing. This is probably the last thing we do besides the amines and amides, is arrange the compounds from least oxidized to most oxidized. So least oxidized means most reduced. Keep that in mind. Any answers? C. And yes, the answer is C, not A. Yeah, okay. So if you look at 3, so the least oxidized, which is the most reduced, no oxygens at all, 3 is the winner. Then you're looking for 1 oxygen. And all right, you have a tie between 4 and 3. But we know that this double bond oxygen kind of counts as 2 oxygens. It counts as like 2 bonds to an oxygen. And also we saw that when we oxidize an alcohol, we get to a ketone or an aldehyde. So that means 4 will come next. Then 1 will come after that. And then 2, since it has the most oxygens, will be the most oxidized. So wow, look at that. Pearson got it right. Good job, Pearson. Okay. Then we have another one called ethers. So ethers are just like alcohols, but they're alcohols without the H, and then you have two random R groups on the end of it. Nothing really too special there, but they have. And the thing is, the way you say it is the way you name them. The O is like your focal point. You want to look at what's on either side of the O. If you have a methyl on one side and a propyl on one side, it would be methyl propyl ether. So it's whichever one is in alphabetical order. So here's an example of that. On one side, you have an ethyl. The other side, you have a methyl. So it would be ethyl methyl ether. That sounds funny, but it would be ethyl methyl ether. Then you have another one where you have two ethyls, one on each side, diethyl ether. Even more difficult to say. So that's how you name your ethers. So it's usually the one R group, the second R group, then your ether. Then you write the word ether. It could be benzyl, propyl, ether, or bromo, benzyl, ether. I know it's a tough language, but we'll do examples. Here, we'll do an example right now. So let's do 1, 2, 3, like that. And we have an oxygen. Then we have one. Here we go. Do that. Okay. So what would that be called? So you have an oxygen in the middle. So you know it's an ether. So ether comes at the end. And then what on one side you have what? What is this element? You guys know that one. Chloride, right? So it would be, what would be the prefix for it here? Chloro, good. So it would be chloro. And then what is this? Attachment. How many carbons is that? No, it's not 4. 1, 2, 3. This is not a carbon. It's just a bond to the oxygen. 3. So what's 3? It's okay, Christina. 3 is something that you know, not ethyl. Ethyl's 2. Trying to look. Somebody got this. Let's see. Not methyl. Methyl's 1. Prop. Good, Tariq. Good. So propyl is 3. So it would be chloropropyl ether. And that's what the name would be. So yeah. Okay, any questions on this? No? All right. Cool. So we have ethers. Ethers have low boiling points because they partake in less interactions than the other ones compared to, I mean, they're less electronegative for the most part because usually they have longer chains. Yeah, once you guys learn the names, you'll be fine. All right, so then to wrap it up, we have amines. So in organic chemistry, whenever you see the prefix or whenever you see the letters AM, amine, amino acid, amide, there is nitrogen involved. So ammonia, that means there's nitrogen involved. So an amine is basically any organic compound derived from just one nitrogen. So you can have primary, secondary, or tertiary amines, and usually they're bases like ammonia is the simplest amine. So you already know one of them, NH3, and you basically name what's attached to it, and then the amine after it. And yes, they're weak bases because of nitrogen, right? So think about them as derivatives of ammonia. So they're all in the same class of ammonia as weak bases. But the more complex they are, the more weak the base is going to be. So here's ethylamine. And then there's a common reagent that we use in the lab called TEA, like T. It's called triethylamine. So it's just like ethylamine, but instead of these hydrogens, you have two other ethyl groups. So these CH2, CH3, you have two of them in addition here. So it's called TEA, triethylamine. And that's also a weak base used for different buffers and stuff like that. Then you have, this is ethylmethylamine. So it's a secondary amine, meaning secondary means it has two bonds to non-hydrogen components. So that's the ethyl right here and the methyl right here. So it's just, guys, I think it's just a matter of doing the homework and knowing the name. So here's what we're going to do. So hold on, I'm going to, all right. So then the last thing is amines can react with carboxylic acids. Oh no. And what can they make? They can make a new functional group that the chart in the slides forgot to mention called an amide. So an amide is, let's say you add, here we go, we're adding a carboxylic acid to a amine, and we're creating, this is R prime and this is R. And then what's going to happen is this hydrogen will go away. This carbon, or sorry, this hydrogen will go away also. This oxygen will attack this nitrogen. Oh, wait, no, the carbon will attack the nitrogen. Yeah, carbon will attack the nitrogen. The water will come out. This water will come out. And this is how amino acid chains and proteins are made. So this is peptide synthesis, it's called. So a water molecule leaves, and it's called dehydration synthesis because it's losing water. And then the electrophile, which is the carbon, will find the nucleophile, which is the nitrogen. And then it would end up like this. R, C double bond O, N, H, R prime, like that. And that's the base of an amino acid. So over here you have whatever the side chain is for that amino acid. And then going forward there, you have more stuff. You have another carbon and then so forth. Okay. So I would say don't worry about naming amides or anything. Just worry about naming the amines for the nitrogen-containing functional groups. Okay, so that wraps it up for that, and we'll stop the recording here.